We move on to another important concept, which is electric flux. We define the electric flux as the product of the area by the electric field. So here you have this area A and this field penetrating the area E. So we define the flux as EA. EA, that would be the number of field lines, going from this area. We use the Greek letter phi for flux. So here phi E stands for the electric flux, and it is equal to EA. In the SI system, E is measured in a Newton per Coulomb, and A, the area, is measured using meter squared. If the area was not perpendicular to the field, then there is an angle. So now we have to take the component of the field that is normal to the surface. So we have E cosine theta, that is the component normal to the surface. And this way the flux now is EA cosine theta. Another way to look to this is to represent the area by a vector. And the vector A that represents the area will be perpendicular to the surface in direction and in magnitude equal to the numerical value of the area. So this way, we say that E multiplied by A cosine theta, where A cosine theta is the component that is penetrated by the field, that is perpendicular to the field lines. So in general, the flux, the electric flux, is EA cosine theta when the normal to the surface, the area vector, and E are parallel, so theta is 0 and cosine 0 is 1. Calculate the flux of a constant field 5 Newton per Coulomb in the z direction through a rectangle with area 4 square meter in the xy plane. So the area is in the xy plane and the field is in the z direction. What would be the flux? Which one?
Sorry, I was reading again.
Yeah, take your time.
You would have to multiply it by the meters, right?
Yes, yes.
So it will be number 3.
Thank you. Yes, because z is perpendicular to xy. Z direction is perpendicular to xy, right? So in this case, all the area is penetrated by the field, and it is simply 5 multiplied by 4. Calculate the flux when you have the electric field tilted 60 degrees away from the positive z direction through a rectangle, again with the same area in the xy plane.
Would it be 2?
Yes. So now you need to take cosine 60. Cosine 60 is 1/2. Okay. So it would be 2. As you can see from these examples, the flux can be maximum when theta is 0, can be minimum when theta is 90 degrees. In that case, the field line will be parallel to the surface, not penetrating the surface. And that situation, the flux would be 0. But for this situation with 60 degrees, it would be 10 Newton meter squared per Coulomb. Now, to calculate the electric field, we use Coulomb's law as we did before when you deal with point charges or a system of discrete charges, as we call it. But there is another way to calculate the electric field, which is to use Gauss's law. Gauss's law. Gauss's law simply relates the electric flux from a Gaussian surface to the charge enclosed within the surface. So here, if you take this situation, have this charge, and the electric field at distance r will be kq over r squared. So the flux from this spherical surface, it would be EA, and A is just 4 pi r squared. The area for a sphere is 4 pi r squared. Okay? So E is kq over r squared, and the area is 4 pi r squared. Okay? K, 9 by 10 to the power 9, is expressed as 1 over 4 pi epsilon naught. Epsilon naught is called the permittivity of free space. It is 8.85 by 10 to the minus 12 coulomb squared per Newton meter squared. So from calculating the electric flux from a closed surface, we can calculate the electric field. In general, the flux from any surface is equal to Q divided by epsilon naught. Q is the charge enclosed in the surface. Epsilon naught is the permittivity of free space. Okay. So if Q is 0, if Q inside is 0, then the flux is 0. If Q inside is positive, the flux is positive. If Q inside is negative, the flux is negative, and so on and so forth. Consider this situation. Find the flux through the surface. You have inside the surface 2 coulomb positive, minus 3, minus 5 negative. So the net charge would be minus 8 plus 2, it would be minus 6 coulomb, right? The flux would be minus 6 coulomb divided by epsilon naught. For a closed surface through which the net flux is 0, each of the following statements could be true. Which of the statement must be true? There may be more than one. There are no charges inside the surface. This is a possibility because it says the net flux is 0. The net charge inside the surface is 0. That's a possibility. The electric field is 0 everywhere on the surface. The number of electric field lines entering the surface equals the number leaving the surface. So B and D must be true. The net charge inside must be 0, and the number of field lines entering and leaving must be exactly the same in order to have 0 flux. The electric field is 0 everywhere on the surface. This is a possibility, but this can result from having a field inside and field outside, okay? Not necessarily 0 flux. So B and D would be the right answer for this problem. We apply Gauss law to derive the electric field for situations where we have symmetry of charge distributions, like this example. When we apply Gauss law here, we derive the electric field to be sigma over 2 epsilon naught, and sigma is the charge density, charge per unit area. So this conductor will give us sigma divided by 2 epsilon naught, and this surface another sigma divided by 2 epsilon naught. The field here is going into the conductor, here out of the conductor, so the two fields add up. Sigma divided by 2 epsilon naught plus sigma divided by 2 epsilon naught, they add up to sigma over epsilon naught. This is the field inside. Outside here, if you take this region, the field due to the positive plate will be going out. The field due to the negative plate will be going in this way. so the field is 0. If you take this region, again, from the positive charges, the field is going out. For the negative charges, it is going to the negative charges, so the resultant is 0. So outside the region between these two plates, outside the field is 0. Inside, it is sigma divided by epsilon naught. This is called a capacitor. We will learn about it more details in coming chapters. So inside the capacitor, there is a value for the electric field. Outside the capacitor, the field is 0. The diagrams below show two uniformly charged spheres. Uniformly charged sphere. The charge on the right sphere is 3 times. The charge on the right sphere is 3 times as large as the charge on the left sphere. Which force diagram best represents the magnitudes and directions of the electric forces on the two spheres? Any suggestion?
I think it would be number 5.
Number 5.
Yeah.
Well, you need to think again.
No.
I was thinking it would be
I don't know.
4, but I don't really understand.
Okay. We have two charges, Q1 and Q2. The force between them is a property of the two charges. It's not a property of one charge, right? So this would be the answer. This is very much similar to the situation that we discussed earlier. We don't care which one is bigger, because the force, this force is KQ1 Q2 over R squared. This force is KQ1 Q2 over R squared, right? We are talking about electric forces, right?
Right.
Go back to Coulomb's. The force is KQ1 Q2 over R squared. So the force contains both Q1 and Q2. And according to Newton's third law, the action-reaction pair of forces. Forces are equal in magnitude, opposite in direction. Because they are positive, so it's a repulsive force. But the magnitude is going to be the same. Right? You understand it?
Yeah.
Thank you.
Yeah.